In this example, we are analyzing a silicon bar that has been doped with donor impurities at a concentration of 2.25 times 10 to the power of 15 atoms per cubic centimeter. We are also given that at a room temperature of 300 Kelvin, the intrinsic carrier concentration of pure silicon is 1.5 times 10 to the power of 10 per cubic centimeter. Assuming that every single donor atom is ionized, our goal is to find the resulting equilibrium concentrations for both electrons and holes in this N-type material. To find the equilibrium concentrations for electrons and holes, we will start by calculating the electron concentration using the donor concentration and the intrinsic carrier concentration. Given that every donor atom contributes one free electron, the electron concentration can be approximated to match the donor concentration under complete ionization. Consequently, we analyze how this affects the hole concentration generally derived from the principle of charge neutrality in the N-type material. To find the answer, we look at the two types of carriers separately. For an N-type semiconductor, the concentration of free electrons, which we call N0, is approximately equal to the donor concentration we added. This is because the donors provide far more electrons than the pure silicon naturally would. To find the concentration of holes, which we call 0, we use the mass action law. This law states that the product of electrons and holes must always equal the square of the intrinsic concentration. By rearranging this, we find that the hole concentration is equal to Ni squared divided by the donor concentration. Now we plug in our given values. We take the intrinsic concentration of 1.5 times 10 to the power of 10 and square it, which gives us 2.25 times 10 to the power of 20. We then divide this by our donor concentration of 2.25 times 10 to the power of 15. The 2.25 terms cancel out, leaving us with a final hole concentration of 1 times 10 to the power of 5 per cubic centimeter. Our electron concentration matches the doping level, and our hole concentration is much lower. With these calculations completed, the scientist reflects on the implications of the results. Understanding the balance between electron and hole concentrations is crucial in semiconductor physics, impacting how devices function. Each number tells a story of potential paving the way for advancements in technology that rely on precise doping levels.